Thank you for the nice introduction. And oh, sorry, I'm losing the microphone. Give me just a second. So I hope it holds now. Yeah, and thank you all for being here. Thanks to the ESI and the organizers for this beautiful conference. In my short talk, I want to present you some conceptual overview and results on my PhD project together with my advisor, Roland Donninger, in which we focus on two prototypical geometric wave equations, namely the wave maps equation on the one hand. How do I get the laser pointer? Right. Okay, so the first model equation is the wave maps equation for a wave map U, which is defined on 1 plus d-dimensional Minkowski spacetime with target the d-sphere embedded as a submanifold into d plus 1 dimensional Euclidean space. And you can view this as a nonlinear generalization of the scalar wave equation. And the geometry of the target somehow induces the nonlinear structure of this wave equation, of this wave maps equation. And we're going to consider this for a special subclass of wave maps, namely the so-called corotational wave maps, which respect the rotational symmetry of the target and the domain. Yes, and the evolution then basically reduces to the evolution of this polar angle psi, which is a radially symmetric function. And one obtains then a semi-linear wave equation for this psi under this corotational reduction. The second model that we're considering is the hyperbolic Yang-Mills equation. That's an equation for a connection 1 form, A mu, also defined on d plus 1 dimensional Minkowski spacetime with values in the d times d skew symmetric matrices. And associated to this connection 1 form, one has the connection 2 form, the curvature 2 form, F mu nu, and the Yang-Mills equation asserts that the covariant derivative of this curvature 2 form is 0. So the Yang-Mills equation is a sort of nonlinear generalization of Maxwell's equations. And again, we're considering the Yang-Mills equation for so-called corotational Yang-Mills connections, which also basically reduce to the evolution of a radially symmetric function. And as for any kind of equation, any type of equation, an important concept for the solution theory are the symmetries and special solutions. And as we have seen in other nice talks already today, yeah, there are some scaling symmetries. Both the Yang-Mills equation and the wave maps equation do enjoy a scaling symmetry. And solutions that are invariant under the scaling symmetry, they play an important role in the description of the breakdown of solutions. So solutions which are invariant under the scaling symmetry, they are called self-similar. And for both types of equations, self-similar blow-up solutions are known explicitly in closed form. Their existence was proved back in the late 80s and 90s. They were then found in explicit form in 3 and 5 dimensions, and the higher dimensional analogs were then found in 2015 in closed form. So for a fixed, arbitrary but fixed time capital T, one gets here an explicit solution in the corotational class, which has a blow-up at the origin. So if you are at x equals 0, you see that this solution will blow up as time approaches the blow-up time capital T. And the same singularity formation, so the same breakdown of solution you will observe for this Yang-Mills connection here, where A and B are constants which depend on the dimension. And now the pressing question somehow is this just a coincidence? Are both solutions just some coincidence? Or is there a larger class of solutions where this type of blow-up of singularity formation is observed? And in order to address this question, we inquire about their stability in the PhD project. And one remarkable feature that I have to stress out about these solutions is that the blow-up only occurs at the origin. So only at x equals 0 you will see the blow-up, and everywhere else this solution is perfectly smooth and well-defined, which means in the dynamical viewpoint, as if you view this as an evolution or as an evolving solution to the equations, that both solutions continue to exist even after the blow-up, which is very remarkable. And in the project, we address the stability of both solutions in space-time regions beyond the singularity. To be more precise, what do I mean by this? We consider the following space-time regions, omega of kappa. This is the gray shaded region here in Minkowski space-time. For instance, kappa equals -1 would correspond to the backward light cone of this blow-up event here. Kappa equals 1, would correspond to the full exterior of the future light cone of the singularity. And we are asking about the stability of the wave maps flow and Young-Mills flow near those solutions within this whole region here. And somehow conceptually, the stability problem is described by the following. So what are we doing here is we're prescribing data which are in some sense near to the blow-up solutions, which blow up at time 1. We perturb them at the initial time slice t equals 0. Then all the hard analysis and so comes into play. Unfortunately, I don't have time to go into the details. Then we evolve them within this region and prove that the solutions that we get within this region somehow converge back to this to the blow-up solutions that are known explicitly. So that within this region, the solutions again that start from data near the blow-up will converge back to the blow-up for some time, which is close to the time 1. So let me just briefly mention that there are, of course, lots of results on the stability within the backwards light cone. So this was pioneered by Roland and his research group. And right, in order to access regions beyond the backward light cone, what do we do? So what's the idea to access, to go from within the light cone, beyond the light cone, and outside of this region? And the idea is to introduce similarity coordinates, so-called a novel set of similarity coordinates, which have fantastic features. So they are really magnificent, I have to say. So they are of this special form, and the only thing which determines the geometry of this of the coordinate system is this so-called height function h. So by there are some elementary conditions on the height function that you can prescribe in order to go beyond the time of blow up here and look beyond this time, what happens there, and track the evolution then there. So that's the first nice feature, that it covers this whole region. Another feature is that it is very well compatible with self-similarity. So their structure scales very well with the self-similar scaling and the scaling behavior of the equations. It is well suited to detect stable blowup, of course. Then what else? The time slices, the tau slices, they are drawn here. These are these self-similarly shrinking time slices. They are space-like hypersurfaces, which means that they are very well suited to the wave evolution. So you can very naturally study the wave evolution in this coordinate system and get full information on the flow inside this region here. So they have been first implemented in some hyperboloidal setting for some hyperboloidal height function h by Roland and Birgit for the three-dimensional wave maps problems, and later on in my first project with Roland for the Young-Mills equations in odd space dimensions. Good, and with this, without going into further details, let me actually come to the stability result. So what we're actually proving, how does this look like? So this would be the, I will go through this and then I'm done for today. So this will appear very, very soon, I promise. And basically, what we're proving is the following. So in any space dimensions, without any restriction on oddness or so, where the blowup exists, we fix a regularity k, which is, okay, I have to say an integer regularity strictly above the critical one. Then we fix some constant r, which gives you the size of the support of the perturbations for the initial data. So for any size of perturbation of the initial data, we consider then the region, this gray shaded region. Then we prove the existence of some constants so that any smooth corotational initial data f and g, which are outside of this ball of radius r, coincide with the blow-up solution that blows up at time equals 1. Inside this ball, we have some smallness condition in a Sobolev norm. So the whole Sobolev norm of the initial data compared to the blow-up is small. And then we infer a blow-up time close to 1, close to the blow-up time where we perturb, and a unique corotational wave map. It's again a corotational one, which is smooth within this extended region with target into the sphere, which has those initial data, and it converges. This is somehow then the stability result. It converges to the explicit blow-up solution at this time t star in a Sobolev norm along those space-like hypersurfaces from the previous slide at this given rate. So this is the stability result for wave maps. The same is true adapted to the Young-Mills equation, and yeah, that's all for today, and thank you very much for your attention.